Hi everyone, in this video we're going to discuss optimization, which is not necessarily confined to inverse problems as a subject, so it's sort of switching tacks here for a little bit and then we'll go back to sort of prototypical inverse problems. But the reason why this is important in the context of inverse problems is because remember a few videos ago we talked about recasting Tikhonov regularization in terms of a least squares optimization problem. It turns out that optimization is really what we want to do because it gives us the most general object to look at. So at the end of the day, we want some function phi that defines a misfit between our data and our model parameters within our model. And we want to minimize, we want to find that model parameter that minimizes this misfit phi. In general, phi can be nonlinear, so we need general optimization methods. And these typically fall into two categories, first and second order methods. Generally, good to keep in mind is that on the one hand, first order methods are slow, but they are stable and can have provably can be shown to be provably convergent. Whereas second order methods are faster in general, but they are less stable. Another good thing to keep in mind is that optimization in and of itself, finding a global optimum, is an NP-complete problem. So in general, the best we can hope to do is get a local minimum. So with that being said, regarding first order, just think gradient descent or stochastic gradient descent. Stochastic gradient descent is basically just gradient descent, but you add an extra term that's random, hoping that you'll pop out of a local minimum. But again, like I said, it's global optimization's NP complete, so you're not guaranteed to do that, but it at least gives you some probability of not getting stuck in a local minimum. That's the idea behind stochastic gradient descent. And as far as second order methods, you want to think Newton's method. So this uses a second order approximation using the exact Hessian. Quasi-Newton methods, because the Hessian can be expensive, and you might not want to store it either. There's also quasi-Newton methods that use an approximation of the Hessian. And then finally, I put a star by 2C, which is inexact Newton, Newton-Krylov, Newton-CG. The main idea behind these is that you don't solve the system for the step involving the Hessian exactly. And I put a star by this because this is the one I'll really try to focus on in this series, because this one I think has probably the most, it's the most flexible, fast converging method, but that'll be a few videos from now. So for now in this video, we'll talk about gradient descent and the Wolfe conditions. So gradient descent in its vanilla form is just the following. You give an initial guess x0, and then you update your guesses according to the following rule. You have some step length alpha. You go in the negative direction of the gradient. Why? Because the gradient is the fastest ascent direction of f, and so you want the negative sign to descend. And that's all there is to it, really. Stochastic gradient descent is xn plus 1 equals xn minus alpha n gradient of f of x n plus a random term here. And the idea there is that if I give you a function that looks like this, say, and I start stepping, the gradient's going to tell me, okay, now my gradient has hit 0. And so I might do a bunch of steps here, but then this random term might randomly shoot me up to here. Oh. Onto this point. No, not this one, because that would still be in the same Bayesian interaction. So just randomly, I might jump from there straight to there, And now I'm catching this basin of attraction here, and then I just got lucky, and that ends up being the global minimum there. And not necessarily global, but at least a better local minimum in the optimization landscape. So that's all there is to stochastic gradient descent. We won't talk too much more about it in this series. And so let's just go through a simple example with gradient descent that can help illustrate the Wolfe conditions to us. So let's look at f of x equals x squared. So it's just this quadratic function, and we have a global min at x equals 0. And let's take an initial guess at x equals 1. And we're going to just take a constant step length. So in general, the step length can vary with the actual step that you're taking. In general, you want to take smaller steps as you get closer to the minimum. But let's just say we're doing constant here. In this case, we can explicitly compute what the nth step looks like, and it's just 1 minus 2 alpha to the nth power. Now, let's look at different step lengths. So the Wolfe conditions are all about these step lengths alpha. So if we choose alpha equals 1, we get the following. We get 1 minus 2, parentheses, all to the n, which is negative 1 to the n. So what this amounts to is we start here. We say, okay, well, the gradient at this point, right, this tangent is positive, so we're going to go in the negative direction, the opposite direction of the gradient, to descend. But we took a huge step length, and we ended up back over here. And then now we're here, we take a negative, we now have a negative slope, so we want to move in the positive direction. We take this point, and we step right back to where we were, and there's no descent. We're always at f of x equals 1, and so we don't converge to a minimum here. In contrast, if I take alpha equals 0.1, well, I'm going to see, again, positive slope on this tangent, so I'm going to move in the negative direction, and I'm going to build the sequence. I'm going to move a little bit here, and then again, I see positive slope, so I move in the negative direction, and I continuously descend. And in this case, I'm actually going to hit the global min. Why? Because I'm going to get 1 minus 0.2 to the n, or 0.8 to the n, which goes to 0, obviously. And then on the other hand, if I take alpha to be really small here, like 0.001, I do get convergence. This ends up being like 0.99 to 8 to the n, which goes to 0, but very slowly, extremely slowly. So the problematic cases are the following. This first case where we don't converge at all because we took massive time steps, and we never even descended on the function even. Because we took such a large time step, basically, or a step length, that we no longer were capturing the local behavior of the function, right? Because we computed the gradient to be, in this case, it would be, what, negative 2, right? Because derivative is 2x, and 2 times 1. But we took a large step length such that we're nowhere near approximating that. So we end up getting unlucky by being too aggressive. We end up over here, and then we don't even descend. So the gradient is just not accurate with that sort of step length. So the first case, we want sufficient decrease, which if we're aggressive and take large time steps, we can do better, but also we lose the local behavior and we don't decrease enough. On the other hand, we can also take too small of time steps there too. That ends up that being the case as well. So the other, well, actually, yeah, disregard that last comment, because ultimately the Wolfe conditions will scale with respect to the time step, right? Or not the time step, the step length. And then the second one is that we want to avoid too small of steps. Because here we saw that, you know, ultimately the slope here is, the slope at these other points are still negative, so we can be more aggressive than this. So the Wolfe conditions, the first one is the Armijo condition, and this one talks about sufficient decrease. So I'm going to define phi of alpha to be the following. We're assuming that our point xn is fixed and that the search direction that we're looking at is also fixed. And all we're trying to figure out is a step length alpha that gives us a good answer. So in the context of gradient descent, this is negative gradient of f of xn. As we'll see with Newton methods, we can choose different search directions. So the Armijo condition is just the following. Where we go upon step length alpha must be less than or equal to where we started, plus sort of the local expected. So this is what would pop out in your Taylor expansion, right? But we can scale with C1 because of course the Taylor expansion is a local property. And so we just want to capture that local behavior in the Taylor expansion. So we have this C1 that's sort of how aggressive are we going to be with it. And so typically you can choose pretty aggressively on the order of 10 to the minus 4, and that's citing no Sedal. That's sort of what he said is sort of standard. You can choose C1 quite small. And so just to illustrate this, what this says is that if I'm starting here at xn, that's my functional value there in purple. I pick a slope C1, and again, this is user defined of how aggressive you want to be. And this slope, we draw this line with slope negative C1 because ultimately this Pn has a negative in it. Otherwise, you're not even trying to descend. And then we just say, okay, well, those step lengths, so I'm plotting now alpha on this axis. Whatever the function value is, it must be below this line. So these green circles are acceptable points, and the red x's are unacceptable. We throw them out. So it violates the Armijo condition, so we're definitely not choosing that step length. To avoid small time steps, or not time steps, avoid small step lengths in the optimization, we satisfy the curvature condition, which says that the slope at our step length alpha must be less than or equal to some constant, C2. Oh yeah, sorry, I forgot to mention. C1 must be between 0 and 1. Why? Because so we don't want to go to 0 or above it, right? Or below 0, because think about 0, right? All that we say then is that it's less than or equal to 5, 0, but who cares, right? This could be less than, this could be exactly equal to 5, 0, in which case we're not descending at all, and we end up in the same condition we had over here, where we don't descend at all. We just keep going. F of x equals 1, 1, 1, 1, 1, 1, and so on. And then we don't want to go above 1 because the point is that's our expected local behavior. And so we shouldn't scale above that. As for the curvature condition, C2 must be greater than C1. I actually don't have great intuition why we need this exactly. I'd have to think more about that. I'll make a comment in a future video if I figure that out. But regardless, C2 must be greater than C1. And what this says is that the slope at alpha is less than or equal to some constant, again, that we tune, times the slope of the original point. So here, this is roughly the same curve up to, my drawing ability. We check the slope at our point xn, and then we rotate it up according to some theta. Theta here, if you want, you can write C2 equals cosine theta or something like that, where theta is then strictly between, the arc cosine of C1 or so not. But regardless, you can view it as taking this line, and I think geometrically it's easier to see that's just a rotation, but you're scaling it by this C2. Now you draw this line here, and then you go across each point in the domain, and you check its slope. So here, this red dot is unacceptable because its slope is steeper than this. And so intuitively what this says is, hey, look, dude, keep going. Take your step length further because its slope is steeper than this cutoff that you set, which means that if you take a longer step length, you're gonna decrease even more. Similarly here, it's gonna have a steeper slope than this one we've drawn, and so on until we get here, and just in the eyeball norm, that's roughly the same. So here, and we say, okay, well, that's acceptable. Hey, look, we can still descend, but not that much. So let's just, we'll say that's acceptable, and so on. And then, so then if the slope goes positive, right, we definitely are going to do that, right? We say, okay, that's acceptable because, look, hey, this, if you go further, you're actually going to increase the function, don't step further. And similarly here, and again, the slope gets too steep. And so now in this case, this would be worse. Well, actually, no, it wouldn't, right? Because this actually goes below this local minimum. But it's saying, hey, look, the slope is negative, keep stepping. And so let's go back to original. So those are the two conditions. Let's look back at what exactly happened in that first case. So let's look at Armijo first. So we're taking f of x equals x squared, xn is 1. Pn is the gradient at 1, which is negative the gradient, which is negative 2. And so phi of alpha is just 1 minus 2 alpha squared. So let's look at the Armijo condition. That says 1 minus 2 alpha squared is less than or equal to phi of 0. Phi of 0 is 1 minus, okay, so that's the gradient of f squared, which is minus c1 alpha, minus 4c1 alpha. Okay, and let's plug in alpha equals 1. That's 1 is less than or equal to 1 minus 4 alpha c1. Which is false. So the Armijo condition is violated. And remember, so that means not decreasing enough. Which again, in this case, this was the case where we were bouncing from 1 to negative 1, back to 1. So the f of x is just 1 the whole time. We're not decreasing at all. So of course we're not decreasing enough. So in this case, the curvature condition should be not satisfied for this case. So let's look at alpha equals 0.001. So phi prime of alpha is minus 4 times 1 minus 2 alpha. we want phi prime of alpha, is less than or equal to C2 phi prime of 0. Phi prime of 0 is -4. -4, 1 minus 2 alpha is less than or equal to C2. Oh yeah, so sorry. Notice that this is true for any C1 because C1 is strictly greater than 0, right? So it's 1 minus something. So 1 certainly can't be. It's always false, no matter what C1 is. Phi prime of 0 is -4. So it's -4 times phi prime of 0 was a -4 times C2. So let's divide by -4, so the inequality flips. C is less than or equal to 1 minus 2 alpha. Okay, so here, so remember that C2 is in this interval. So C2 is less than or equal to 1 minus 2 times 0.0001, 0.9998. And so that means that the curvature condition is extremely non-restrictive. In other words, it allows for tiny steps. So the only way, so if we chose C2 equals 0.9, then our choice of alpha equals this would be a violation. But the point is, the only way that this is not a violation is if you're being super, super lenient with it. The closer that gets to 1, the more lenient you're being. So thank you all for watching. Those are the Wolfe conditions. And I'll have a few more examples of gradient descent in the next video, and then we'll get into the second order methods. Thank you for watching.